Ciao friends, and welcome to a new video from SQL BI. In this video, I want to answer a question that appeared very quickly as soon as I published an article. The article is about different options to model many-to-many relationships in Power BI and Tabular. Now, if you are not familiar with the article, just go there. The link is below in the comments. Read the article, maybe watch the video, because I'm going to do a very quick recap of the content of the article with the goal of introducing the question from Daniel. So the article is about a new way of modeling many-to-many relationships. I have always been creating many-to-many relationships using a pattern. Let me show you this with the whiteboard. In the model that we use for the demos, we have a customer table, a sport table, and customers play sports. So we have a customer sport table, a bridge table in the middle. And in order to make the filter flow the right way, we need to use a bidirectional relationship here. So the relationship between customer and customer sport is set as a bidirectional relationship. This means that the filter goes from customer to sales directly, but from sport it needs to go to customer sport, then travel to the bidirectional relationship, and finally reach sales. This is the standard way we have modeling many-to-many relationships over time. A new way that I learned during a classroom is slightly different. Instead of relying on bidirectional relationships, and you know that we do not like bidirectional relationships, it uses a many-to-many cardinality relationship between customer sport and sales. Therefore, the filter from sport goes to sales through customer sport, and from customer it goes to sales through customer sport. And it relies on this relationship that, as you see, is a many-to-many cardinality relationship, and it does not need to be bidirectional. This new model has some advantages. Indeed, what we notice measuring performances is that when you filter only by sport sales, everything works pretty well using the canonical model, because it makes a good usage of the storage engine. But when you have a filter that goes from customer and sport at the same time, there is a large increase in the usage of the formula engine. And the reason is this bidirectional relationship that is solved by using some CPU from the formula engine. Therefore, there is a big difference in querying only by sport or querying by sport and customer. On the other hand, when you place the filter only using the customer table, so when you only place a filter from customer, you rely on a one-to-many relationship that is the fastest way of moving a filter between two tables. The new model has a different behavior. The new model is more consistent in the way it uses the CPU, because it doesn't really matter whether you filter by sport or you filter by customer. The time required to answer the queries is always the same. And this relationship, even though it's a many-to-many cardinality relationship, is a unidirectional relationship. Therefore, the usage of the storage engine is much better. And we ended up suggesting to use this new model instead of the old one. But like half an hour after I published the article with my findings, Daniel sent me a question saying, hey, you know what? We could get the best of both worlds if we slightly change the structure of the relationships. Let's look at Daniel's question together.
Hey everyone, this is Daniel, the Tablet Editor guy, and I have a question for the SQL BI team. So I read the recent article about many-to-many modeling in Power BI, and I noticed something interesting about this pattern. So in the article, the SQL BI team suggests that setting up the relationships this way is a clever way to simplify the diagram and avoiding the bidirectional filter. But the drawback is that when there's a direct filter on the customer dimension, that filter will have to now propagate through the customer sport bridge table. So instead of doing that, I'm wondering if we couldn't just get rid of the relationship here and then add a direct one-to-many relationship between the customer dimension and the sales facts. This way, I think that we would sort of get a best of both worlds solution to that problem, but I'm curious to know what the SQL BI guys thinks about this.
Thank you, Daniel. So, as you have seen, his suggestion is to change the structure of the relationships. Now, before moving further, Daniel, I have seen that you are using a whiteboard to explain your diagram. That is cool, but it's kind of legacy. There are better tools that you can use to create your diagrams. One of them, probably the best one in my opinion, is Tabular Editor 3. So I'm going to use Tabular Editor 3 during the demos. So maybe you learn something about this great tool. That's it. Daniel's suggestion is to use this relationship, a different one. So instead of relying on a relationship between customer and customer support, Daniel says, let's get rid of this relationship. We create a relationship between support and customer support using the new model, but then the relationship between customer and sales is a direct one. And both relationships are going to filter the customer key column. So support will filter sales through customer support, customer will filter it directly, and maybe by doing that we get the best of both worlds, because a filter from customer to sales will use this relationship, therefore it will be very fast, and the filter from support and customer support will traverse the longer path. The question is, what happens when both filters are working at the same time? So, time to test it. Therefore, with no further ado, let's jump to the computer and start measuring performance of the new model. I have here Tabular Editor that is already connected with the new model. Therefore, we have customer that is filtering customer support, support that is filtering customer support, and customer support is filtering sales through a many-to-many cardinality relationship. Everything is unidirectional. We already measure performance of this model, and if you are interested, you can jump to the old article and look at that. Now, the suggestion is to create a direct relationship between customer and sales, removing this relationship. So let's do that. We just delete this relationship, and then we create a relationship between customer key and customer key. It's not bidirectional, it's enable, and we just click OK. So this is the new model that we are planning to use. We only need to save everything and then reprocess the model. So let's refresh automatic so that the new relationship is in place. And then we need to start testing performance. Let me look at the queries. Where are them? Okay, we have a set of test queries that we are going to use. This is the first one that groups by, no, the first one only grouped by sport, this one. So let me copy this and paste it here. So the query is going to group by sport and compute the sales amount. Now with the new model, this is going to use the same set of relationships that we were using in the new model. Indeed, you see that we have a filter from sport that goes to customer support and then to sales. I do not expect anything fancy here, just the regular timings that we are used to see in the new model. Let's look at the server timings and increase that a bit. We have all the time that is spent in the storage engine. There is no formula engine involved. 312,000 is the number of milliseconds, and the set of queries, let's go to the bottom layout. The set of queries that is executed in the batch is the usual one. So this timing is consistent with the time required to scan the new model, because as you see, we do not have anything new here. What is interesting is what happens if we apply a filter from customer and sport at the same time, because then we have a filter from sport, customer support, and then sales that goes to customer key here, and another filter from customer to customer key. In the canonical model, this part of the join between the two filters is made by using quite a lot of formula engine. Let's see what happens if we do the same with the Daniels model. So we need to group by sport and then by customer continent. That should be customer continent. Now we have a filter from sport, a filter from continent. Let's look at the measure and then we dive into the details about how it was executed. Takes a while. And we have the first answer, which is kind of good. You see that it takes around the same time that it used before. Let's look at the details of what happened. We have a first scan that grabs the sport and the customer key from customer sport. So this is scanning customer sport and grabbing customer key and sport key. Then we have a second query that is grabbing the customer. Oh, it's grabbing only the customer key from the table that we loaded previously. So here we define table 3, and later we just grab the customer key because we are interested only in the customer key. Then we have a third query that joins a table 4, that is the table we created here, with sales, and it's making a reverse bitmap join. So it is using the customer keys that are present in the customer sport table to filter sales and reduce its content. And then we have the largest query that is retrieving customer continent, sport, and the value of the measure, so the number we are computing, from table 2. Table 2 is table 2. Where are you? Table 2. Oh, it's here. I don't find table 5, table 4. Table 2. Where are you? Table 2. So let me search for it. That's defining table 3. That is defining table 4. That is table 5. Oh, here it is. Table 2 is defined inside the query. So table 2 is computing quantity times net price. Let me copy this code in a new window that is likely to be easier to read. Let's get rid of that. So we do a select of customer continent, sport, the sum of the measure from table 2, inner join table 3 on the customer key, reduce by, and here we have the definition of table 2. That looks like to be the core of the query. A bit smaller. So table 2 is grabbing quantity times net price from sales, therefore it's scanning sales. It's making the join with customer, and that is pretty cool. You see that the join between customer and sales is happening directly in storage engine during the definition of this query, and that is very different from what happened in both the canonical and in the new model, where customer key is in table 5. This is going to reduce the number of rows scanned by the table. So this is scanning sales, and then it's grabbing customer continent here. That is interesting because it means that the engine is using directly the relationship between customer and sales in the storage engine, and sport and customer sport are used in a different query that is used to reduce the number of rows that are read from sales. The interesting part is that we are not using formula engine. You see that we only have 15 milliseconds of formula engine. The degree of parallelism is quite good, and the query is indeed much faster. So it really looks like this new model is getting the best of both worlds. When you are scanning by sport, it is using the bridge table. When you are scanning by sport and continent, it is using both, but both queries are being executed in the storage engine. What about when you query only by customer? Well, in that case, it should be using the direct relationship, so I would expect it to be as fast as the canonical model. Let's check it just to be sure. If we run the query grouping only by customer continent, I would expect this to be extremely fast because we are grouping by customer sales using the direct relationship. So let's run it, and that should be super fast. You see, we have a very high degree of parallelism and only one storage engine query. So this model really looks promising. The only drawback we have is that we no longer have a relationship between sport and customer. Because if you think about the old model, let me go to the whiteboard. In the previous model, we had a relationship. Let's go for the new one, because that was the suggested one. You had the option of filtering from sport customer using the bridge table, because both tables were linked to the customer sport table. That is useful because you have the option of finding how many customers are playing a specific sport or what are the sports played by an individual customer. The reason is both tables are linked through the bridge table. Whereas in the new model, things are different. If we take a look at the new model, there are no longer any relationship between sport and customer, because customer filters sales directly, sports filter sales, and the only table that sits in between the two is sales. Therefore, if we want to understand how many sports a customer plays, we need to query the sales table. This comes with a couple of important limitations. First of all, if we want to join together customer and sport, we need to traverse the sales table, that in our case might be a very large table. Therefore, performance is going to be quite poor, because we need to scan a table that contains 1.5 billion rows in our scenario, only to match the customers with the sport. But worse, from a modeling point of view, the fact that we are missing the bridge table as a real bridge, it also means that if a customer doesn't buy anything, we will not be able to find the sports that the customer is playing. The reason is we use the sales table as the real bridge, and if we do not have rows in sales, then that relationship will be missing. So there are some drawbacks in this model, but luckily we can get rid of them. Think about that. If we still keep the relationship between customer and sport, we will be able to use it. So we can create a relationship between customer and sport, so that sport will be able to filter customer using the customer sport table. Of course, we cannot create this relationship and keep it active. But what we can do is create an inactive relationship between customer sport and customer, and then we activate the relationship on demand whenever needed. So if you need to count the number of sports that a customer is playing, you can just rely on that relationship. If on the other hand you are interested in filtering sales, then you rely on the new chain of relationships. So let's go to draw some conclusions. As you have seen, Daniel's suggestion is quite good. It really results in the best of both worlds. We have the same speed of the new model and the same speed of the old model combined together in a single scenario. It might be useful to create an inactive relationship and activate it on demand by using Calculate, but that is not a big deal. You can easily author code that uses the correct relationship depending on the number that you want to compute. Now, let me tell you, this is what I think is the beauty of the web. I published an article and like half an hour later, I had comments to the article with new and bright ideas that we can test and work together in order to improve the quality of the models we build. Enjoy, Dax!